The GVSU School of Engineering and Dornerworks presents the Dornerworks Asset Tracking Platform. Locating items or people when their whereabouts are continuously changing is a difficult and time-consuming task. Therefore, this senior project was designed to create a functional prototype for asset tracking based on existing trilateration technology created by Decawave.
Using this technology, two-way ranging is done by sending pings between modules and using time-of-flight calculations. For real-time position, trilateration is used.
There are two situations considered in this senior design project. The first situation is called the proximity solution, which involves tracking assets with respect to a specified vicinity.
The proximity solution consists of one base unit and multiple field units. The base unit has three user-customizable distance boundaries for field units. The distance to field units is measured and sent to the mobile application using Bluetooth. Alerts will be triggered on the base unit when field units move out of the user-selected range. These alerts will be both audible and visual.
Upon proximity setup, the user will be able to view the base units within the mobile application once they are powered on. The application connects, then assigns the base unit a PAN ID. Buttons between the field unit and base units are pressed to pair them through the Bluetooth Low Energy. The application then receives and stores the information for each field unit paired to a base unit. Runtime can then occur with at least one field unit and base unit. While runtime occurs, the user will still have the ability to modify range distance and sensing mode. Lastly, the user may power up additional field or base units. Powering off the units will remove them from the system. After the setup has taken place, the base unit will measure the range of each connected field unit and propagate the information to the mobile application. Each field unit will be monitored if it's within the specified range. If not, then an alert triggers on the mobile application. In the background, a battery checker will signal after a timer ends and the low battery alert will appear on the mobile application if a connected device is on low battery. The interrupts allow for a range change on the base unit from a button. An interrupt will also disconnect all field units if the PAN ID of the base unit is changed.
This is the proximity solution PCB used for the field unit and base unit. This board includes optional population for the base unit that adds extra alert hardware not included on the field unit. The central component of this board is the Decawave module, which is used for distance measurement and communication to the mobile app over Bluetooth. A micro USB connector, shown here, is used for powering the device and charging the included lithium-ion battery. Buttons, shown here, are used for selecting between the three distance ranges and to pair together field units and base units. LEDs are used to show the user which distance range is currently selected. Visual and audible alerts will let the user know when a field unit has left the desired distance range. This is done using a buzzer and high-power LEDs. The programming connector is used to flash factory firmware onto the device. The battery connector, shown here on the underside of the board, allows for easy stacking of the PCB and battery inside the enclosure.
To get to the proximity solution on the mobile application, we must select it from the main menu upon app startup. On the proximity page, we see that every base unit that is available to the phone over Bluetooth is displayed. Each of these base units can be expanded to show their paired field units. Each of these base units and field units can be selected, and their fields can be edited. Here we see that for the base unit, you can change the name, short, medium, and far distances, as well as the mode, leaving or entering. Leaving mode of the base unit means that when each tag leaves the range of the base unit, an alert is triggered on the base unit. Entering mode means that when a paired field unit comes within the range of a base unit, it triggers an alert on the base unit.
This is a demo of the proximity solution. As you can see,
there's one LED on showing that this is in the minimum distance mode, which is currently set to 1/2 meter. As Nolan walks away with the device, once he passes the 1/2 meter mark, the LED showing the alert comes on. I press the button to change to the second distance, which is now 1.5 meters. As he walks away there, at 1.5 meters, the alert shows again. I press the button to switch to the furthest distance range, which is 5 meters. Nolan will now walk away with the field unit. At 5 meters, the alert LED shows again. As Nolan walks back, the alert will dissipate. Right there.
The proximity solution utilizes a single device that is flexible to perform as a field unit or a base unit. The ABS enclosure features a cantilever beam locking design with a speaker grill, battery holder, and belt clip fastener holes. The total estimated weight of the custom PCB is 65 grams. The push force of the button is 1.6 newtons. It's less than half the size of a handheld mobile phone and can be assembled in about 50 seconds. The second situation is called the precision solution, which involves tracking the general location of assets within a building.
The precision solution utilizes trilateration to calculate the precise location of a tag. Grids of anchors are assembled to cover an area. Tags communicate with the 4 nearest anchors, finding their direct distance from anchors' fixed positions. Tags then calculate their location. Tag location is then propagated to the gateway, whom publishes the information over Wi-Fi to the server to be viewed in the mobile application.
The user begins by selecting the precision option in the application. Anchors and gateways must be paired with the application using Bluetooth. Additionally, the network information must be set up if this is the first gateway pairing. A warning sounds if the minimum number of devices isn't met. Next, a floor plan must be uploaded to the application. The runtime will begin after these conditions have been met. Devices can be added or removed, the ping rate can be modified, and the network can be updated. All updates must be made within the BLE range or warnings will trigger. After the runtime begins, anchors ping at a user-designated rate. Trilateration ensues after a tag enters the anchor grid. A tag must be in range of a gateway, or else the tag will not show up on the mobile app. The tag coordinates are sent to the gateway, which is then propagated to the server and updated on the mobile app. The tag batteries are then checked based on a timer, and the low battery alert is enabled if the batteries are found to be low. An interrupt will trigger for the system updates from the setup. Next, we'll describe the server. The server is used specifically for the precision solution to the asset tracking device. The server is run using Linux along with PostgreSQL, and the code is written from Python. MQTT communication is used to send and receive messages to and from this server. The processing is split into the following 4 portions: sending and receiving messages over MQTT, managing these messages, processing database queries, and storing each device data. All messages are put into a queue. Data control processes were made to go through each message queue, calling the appropriate scripts to perform the necessary queries. This method of processing messages allows messages to be received and sent over MQTT efficiently. The relevant tables of information include tag configuration, tag location, anchor location, and gateway data.
This is a short demonstration of the server receiving data over MQTT and putting it into the Postgres database. To the left, we have the MQTT listener that receives and shows all MQTT messages that are being sent to the server. And to the right is the PG admin application, which shows all the data inside of the Postgres database. Displayed right here is the tag table and the data that is currently in it. Right here we see that the MQTT messages to clear the databases was sent from the phone. And if we rerun the query, we see that the tag table is now empty, as expected. Right here, a lot of data has been added. The adds all of the tags, anchors, and gateways. If we run the query again, we see that 10 tags have been added. And we can see this on the anchor table as well, and the gateway too.
This three-dimensional PCB model depicts the tag design for the precision solution. The primary component seen on this design is the DECwave module. This module is used on the tag to communicate with anchor units in order to perform trilateration calculations to determine its respective three-dimensional position, which it forwards to the gateway. The key design requirements which are reflected on this PCB include minimization of board dimensions and spacings, and the supply of ample system power for longevity of device use. Additional components contained on this printed circuit board include a programming connector, shown here, for flashing firmware onto the DECwave module, 4 LEDs, shown here, for debugging and interfacing purposes, a right angle mount push button, shown here, for initiating Bluetooth pairing and interfacing, a two-way switch, shown here, for powering on and off the device, as well as 2 battery receptacles placed on the back of the circuit board, shown here, to each hold a CR2477 lithium cell battery. These receptacles connect the batteries together in series so that they may provide ample power to the system to efficiently meet long-term power requirements and goals. This 3D PCB model depicts the anchor gateway design for the precision solution. This design accommodates 2 different population configurations for 2 different devices, namely the anchor and the gateway. This was done in order to reduce the total number of hardware and PCB designs required for the project. The gateway configuration will essentially have all viewed components populated. The gateway design utilizes both the DWM module here and the ESP module here to communicate tag location to the server. Anchor configurations will be placed by themselves within an enclosure and will be powered by the USB connector shown here. Gateway configurations will be placed in an enclosure with an anchor in order to reduce the number of physical node locations in a system. In this configuration, the gateway will receive power via the USB connector and pass it to the co-packaged anchor through the edge connector shown here. Other key components include the DWM1001 programming connector shown here, the diagnostic LEDs and buttons for interfacing the gateway, and DWM modules for Bluetooth pairing and ESP programming.
Here's the starting page of the mobile application. When we select the precision solution, we will be taken to the map page. As you can see, it was unable to connect via MQTT. From here, we can open up the main menu, go to the networks page. This networks page contains the server IP address and MQTT port that it uses for messaging, as well as the network name and password that are required by the gateway to connect to the network. If we change this to the correct MQTT port and select Update, it will save our changes and show that it is connected to the server. Once back on the map page, we can choose to set the dimensions of the map image. Here are the X and Y dimensions of the map image in meters that correspond to the width and the height of the image. Once those dimensions have been set and the device is connected to the server, you can see that devices are starting to appear on the map that indicate where they're at. In each corner, we can see an anchor. Also on this map page, you can choose to add tags or anchors. Here are their corresponding dialogues. Also, if you select on any of the devices, you can see their info, as well as choose to edit them. Any additions or edits to the system are immediately set over MQTT to the server.
This demonstration conveys a single room with one anchor in each corner. One of them operates as an anchor gateway.
There are 2 fixed tags that will be staying stationary during this test, and 1 mobile tag that Evan will be carrying around. Evan will now be walking around the cage holding onto a tag. As he moves, his tag's location will be updated accordingly on the map.
The ABS enclosures within the Precision solution are for tags, anchors, and anchor gateways. They each utilize the same cantilever beam locking design. Fixture stubs align the mating parts in one way, and the PCBs are fastened with self-tapping screws into bosses. The tag is able to be fitted with a belt clip or Velcro for fastening for the asset to be tracked. Both the anchor and anchor gateway enclosures will utilize Velcro to be fastened to walls within a room in a grid fashion. The weight of each unit is under 0.2 of a pound, and 1.6 newtons is the required push force for buttons. The anchor and tag are less than half the size of a handheld mobile phone, whereas the anchor gateway is roughly the same size as a mobile phone. Lastly, each assembly can be completed in under a minute. The main specifications for the project are as follows. The Precision solution must track tags at a minimum distance of 20 feet with a 6-inch tolerance. The ranges of the proximity solution must be able to change to 3 different radii. An alert for a tag must activate when disconnected from the gateway. Both solutions will offer communication of low battery of the devices, and the server must be able to send and receive data. At the time of this recording, the summary of the project performance cannot be done as the project is still in progress. Due to COVID-19, the original project changed by not 3D printing the ABS enclosures, modifying the Decawave development boards instead of creating custom hardware for each of the devices, and the Precision solution became a single-floor solution. However, the mobile application will still reflect the ability to change tracking between floors. The overcome challenges were Bluetooth enabling using Zephyr, using multiple antennae at the same frequency on the same board, UART interfacing and data acquisition from the available API, creating a server with a database while interacting using MQTT, and overlaying selectable images on the mobile application map.